All right, this is a special problems that are contained in section 4.2 multiplication and addition rule. We're asked to find a probability of at least one success. According to our text, the way to go about this, the probability of finding at least one success is 1 minus the probability of 0 successes. We're making use of the complement rule. You see this, so why do we need to do this? Recall the problem I did within the PowerPoint. I had five pictures of children, and the question I asked, hey, what's the probability at least one of these kids attends Brockton School? Well, probably at least one means one or more. Could be one, and then if it's one, is it the first child, the second, third, fourth, or fifth? Is it, if it's two, is it the first and the second, the first and the third, the second and the fourth? We don't at this time know how to find a probability of exactly one or exactly two or exactly three and so forth. We will once we get to chapter 5. Even if we knew that, we'd have to find a probability of exactly one, which is multiple ways of doing that, or two, then we would have to add the probability of two, and there's multiple ways of getting that. So, all that being said, is many times in statistics, it's easier to come at it from the back door, so to speak, using the complement rule. All right, we're going to find a probability of at least one by taking the whole one, subtracting the probability of none. So the very first question here, number one, an unprepared student. They say unprepared. If you studied, your probability of getting a true false question is going to be a lot greater than if you're just guessing. Unprepared student makes a random guess for 10 true and false questions on the quiz. Well, the first thing is probability of getting it right is zero point 0.5. Probability of getting it wrong is zero point 0.5. Second thing is that these events are independent. If you answer true on the first question, it has nothing to do with whether you answer true or false on the second, on the third. These are purely independent, so probabilities aren't changing. So probability of at least one answer correct is 1 minus the probability that none of the 10 were correct. What does none of the 10 correct imply? That all 10 were wrong. Probability of getting it right is zero point 0.5. Probability of getting it wrong is zero point 0.5. So the first one was wrong, and the second, which means we're multiplying, and the third was wrong, and the fourth, all the way out to the 10th one. Now, rather than taking a calculator and multiplying zero point 0.5 times itself 10 times, well, in mathematics, we know to multiply a certain number of times, we're raising it to a power. Zero point 0.5 times itself 10 times is zero point 0.5 raised to the 10th power. But don't forget, you got to subtract this from the whole number one. You're using the complement rule. If you're not familiar how to raise something to the power, there it is right there in your calculator. All right, it's the little, I call it a caret. All right, you put in zero point 0.5, you hit the caret, you put in 10, and then the calculator will raise it to the 10th power and subtract that answer from one. No, it's 0.999. It's almost a sure thing. Given 10 questions, just guessing, probability of getting at least one of those right is pretty darn high. 0.999. It's almost a sure thing. All right. Number two, a study conducted at a certain college shows that 55% of the school's graduates find a job in their chosen field within 1 year of graduation. Find a probability that amongst 7 randomly selected graduates, at least one finds a job in his or her own field within a year. Well, he tells me probability of finding a job 0.455. Probability that the person doesn't find a job is 1 minus 0.55 or 0.45. All right, he doesn't necessarily tell you that. In fact, he doesn't tell you that, but it's easy enough to figure out. Now, what I notice next is we don't have a raw count. He's just giving us percentages. So even if these events were dependent, you treat them as independent because with percentages, there's no raw count. You can't take 0.45 and the next person's probability is 0.44. No, it doesn't work that way. One percentage does not equate to one person. So in actuality, when it gives you percentages, it's actually easy because you can use that same probability over and over again, in this case 0.45. All right, so probability of at least one college grad finding a job is 1 minus that none of the 7 find a job. All right, so it's 1 minus the first person doesn't find a job, and the second, and the third, and the fourth, all the way up to the seventh. Now, these are staying consistent because these are percentages, not raw counts. So we don't have to do any kind of subtracting. So 1 subtract 0.45 raised to the 7th power is 0.996. Okay, so number 3 here. Let's see what we got. A sample of 4 different calculators is randomly selected from a group containing 16 that are defective and 30 have no defects. First thing I see is, well, if there's 16 that are defective and 30 with no defects, there's a total of 46 calculators. Now notice here he's not giving us percentages, he's giving us raw counts. All right, so we're going to treat these just as they are. These are dependent events. Probability of at least one bad defective calculator out of 4 is 1 minus none of the 4 were defective, meaning that all 4 were good. So it's 1 minus the first one is good and the second one is good provided the first one was good, and the third one is good provided that the second and third were good. I'm sorry, the first and second were good. And the last one, the fourth one, is good provided that the first and the second and the third were good. Dependent events. So you have to do some subtracting. All right, so it's 1 minus probability. The first one is a good calculator. It's 30 chances out of 46. I take that calculator out, put it off to the side. Probability of me getting another good one is only 29 out of 45 times 28 over 44 times 27 over 43.832. If you did not subtract 1 from the numerator and denominator, you used 30 over 46 raised to the 4th. Well, guess what? You would have gotten an answer, but that answer on number 3 would have been, I think it would have given you answer A. So it's kind of like what you call a smart test. If you want to do something silly and do it incorrectly, and, guess what? There's your wrong answer, which you'll fall for, and you'll be wondering, how did I get that wrong? The answer was there. Yeah, the answer was there, but it was the wrong answer. These are dependent events, and you got to treat that as such because you have raw counts as opposed to when you're given percentages. All right, number 4, we talked about treating dependent events as independent. We do that when we're given percentages. And we also do it if the calculations become very cumbersome or if the sample size is no more than 5% of the population. All right, so number 4 says in a batch of 8,000 clock radios, 5% are defective. Well, he doesn't tell us exactly how many. Well, we can figure out in a moment, we'll figure out what 5% is. As a matter of fact, 5% of 8,000 gives me 400 defective. Well, now I got to think if 400 are defective out of 8,000, the remaining 7,600 must be good clock radios. All right. So, probability of one radio, these one clock radio. I'm not sure what this put clock radio. I should have put this here. One clock radio out of the 14 is defective. I'm not sure what that word is there. Just ignore that. Is 1 minus the probability that none of the 14 are defective. Right? Probably of at least one of being defective is 1 minus probably at none. Well, what does it mean to have none of the 14 defective? It means that all 14 were good. Now, this would become rather cumbersome, all right? Because the probability of a good radio is the number of good ones you have over the total 8,000. Now, I'm going to do this 14 times, and these are dependent events. Well, then I'd have to go 7,599 over 7,999, then 7,598 over 7,9. You can see I'm tired already, and I haven't nowhere near done it 14 times. Very cumbersome. We catch a break here. And another factor is that 14 is way less than 5% of the 8,000. 8,000, 5% is 400. You're only selecting 14. That's way less than 5%. So we can get away with treating these events as being independent, which means we can use the same probability 14 times. We don't have to subtract 1 from the numerator and 1 from the denominator because it's considered very cumbersome. All right, doing it 4 or 5 times, no, but 14 times, yes. So 1 minus this 7,600 over 8,000 raised to the 14th power, 0.5123. I think in your practice it says 0.512. All right. The next one here, number 5, in blood testing procedure, blood samples from 6 people are combined into one mixture. Well, You're seeing this now even with COVID testing. They're taking a bunch of samples and they mix it all up, and then if the sample comes back negative, they tell you, then they know that everybody who donated blood was negative for COVID. All right. So what's the probability that the mixture will test positive? If one of them, one or more, at least one tests positive, the whole batch is going to test positive. All right. So the probability of at least one positive test is one minus, at least one positive is one minus none of the six samples were positive. All right. So if none were positive, then all six were not positive. All right. None of the six positive means that none of the six were positive. Well, what's the probability of not? If it's 0.11 that you get a positive test, it's 1 minus 0.11, 0.89 that you don't have a positive test, a negative test. So 1 minus. Now, once again, you say to yourself, why aren't I subtracting like I did back in, problem number 3? Well, we're given percentages. I'm not given a raw count. I can't say 0.89 for the first person, 0.88 for the second, and 0.87 for the third. 1 percentage point and one person are not the same thing. So in actuality, I'll say this again: you actually catch a break when they give you percentages because you can use that same 0.89 six times or raise it to the sixth power. All right, so 1 minus 0.89 raised to the 6.5, 503. Let me just go back here for a moment with this calculator. Notice what I did here. All right, I put this in parentheses because I wanted the calculator to take 1, subtract the product of all these. All right, so I had to put it in parentheses. I don't have to put each individual one in parentheses because the calculator is smart enough. It knows how to divide. It knows to divide before it does any multiplication. So, but you have to have a parenthesis around on the ends, an open and a close, because you want it to take 1 and subtract the product of all of this. So just be aware that you really have to get familiar. If you're not spending the time working with your calculator, then comes time for the test, you go, oh, what am I doing? Well, you got to put the effort in. And to be quite honest, looking at people's logins this weekend, especially this was this morning, Monday morning, chapter 4 is the toughest chapter. I'm not just making this up. I can show you statistically where the grades drop because it's a challenging chapter. And we haven't even got to 4.3 yet counting. So if you're not logging in on a regular basis and doing this, I don't know. I wish you luck. All right. Hope this helps.